Okay, so today we'll be dealing with Legendre equation. Legendre. Okay, so the Legendre equation is given by, the formula for the Legendre is given by y of x is equals to the summation of from n equals 0 to infinity a subscript n x raised to the power of n. So this is the formula, this is the series for Legendre equation. So let's expand the series. Let's put it in series form. So y of x is equal to, so when n is equal to 0, wherever you see n, you make it 0. So a subscript 0. Now x to the power of 0 is 1. So a subscript 0 plus, when n is equals to 1, when n is equals to 1, wherever you see n, you put 1. So you have a subscript 1 x. In subsequent ones, you'll be having when n is equals to 2 and when n is equals to 3. You have a subscript 3 x to the power 3 plus, sorry, when n is equals to 2 and when n is equals to 3, you have a subscript 2 x equals to a subscript 3 x to the third, then continues like that till infinity. So this is the Legendre equation. So, and how can we know how to use this Legendre equation to solve an ordinary differential equation? That is what we are going to learn today. So all Legendre equation must be in this form. All the Legendre equation must be in this form. 1 minus x squared y prime prime minus 2xy prime plus alpha brackets alpha plus 1 y is equals to 0. So whenever you see any equation related to this form, that is how you know that I'm going to use Legendre equation to solve it. So our aim in this Legendre equation is to find our y prime prime, our y prime, and our y. So when we find these differentials, we are going to use it to impute into this equation. From there, we can get our recurrence relation from the Legendre equation. So how can we get our y prime and our y prime prime? If you look at here, the general series for the Legendre equation is given by summation of n equals 0 to infinity a subscript n x raised to the power n. So what you have to do is to differentiate this summation. Okay, so differentiating for the first time, we have that the y of x, for me to differentiate the y prime of x is equals to the summation of from n equals, I will tell you what you are going to write here later, to infinity. So normal differentiation rules, which states that when y is equals to x raised to the power of n, dy dx is equals to, use the power to multiply the x and of course subtract 1 from the power. So you have n x raised to the power n minus 1. So what I just did here was to use the n to multiply the x and of course subtract 1 from the power. So with this principle, I will use that same method to differentiate this term. So the n will multiply everything I have here. So I have n a subscript n x raised to the power n minus 1. So our question now lies on, where is the limit going to start from? Is it going to start from 0 or is it going to start from 1? So I want to note that whenever in Legendre equation, whenever you differentiate with the first differential, your n must also increase to 1. Whenever you differentiate to the second differential, your n must also increase to 2. Because if we should take the limit as it is here, and I try to form the series, you see that if n is equals to 0, this entire series does not exist. So the entire series exists only from when n is equals to 1. So when n is equals to 1, this is how the first differential will be. So let's differentiate the second one, because this one will be applied here, and of course the second differential, y prime prime of x is equals to summation of, so as I told you earlier, when you differentiate the first term, it's going to be n equals 1. But when you differentiate the second term, it's going to be n equals to infinity. So as we did in the previous one, the power will multiply the whole term, and we of course subtract 1 from the power. So if we should do that, we have n brackets the entire power, which is n minus 1, a subscript n, x raised to the power of n minus 1 minus 1. Of course, n minus 1 minus 1 will give me n minus 2. So we are going to apply the value of our y prime, and of course our y into this Legendre equation to get our recurrence equation. So by application, we have that from the Legendre equation, we have that y1 minus x squared. So it's being multiplied by y prime prime, and of course y prime prime is given by some function summation of n equals to infinity n bracket n minus 1 a subscript n x raised to the power n minus 2. Then we move over to the next one, negative 2x is being multiplied by y prime, and our y prime of course is the summation of n equals 1 to infinity n a subscript n x raised to the power n minus 1. Then the last but not the least is plus alpha bracket alpha plus 1 is being multiplied by our y, and our y is summation of n equals 0 to infinity a subscript n x raised to the power n. All these is equals to 0. So what we have to do here is to expand. Let's expand these brackets and of course do the needful. So by expansion, this whole summation multiplies this, and this whole summation multiplies this. So by expansion, when this whole summation multiplies 1, of course, it will still give us the same thing. We have n equals 2 to infinity n bracket n minus 1 a subscript n x raised to the power of n minus 2. So when this summation multiplies this negative x squared, we have negative x squared summation of n equals to infinity n bracket n minus 1 a subscript n x raised to the power n minus 2. So from here, of course, one of the laws of summation is the constants can actually enter into the summation. So it depends. If you like, you can leave the constant outside. If you like, you can still take the constant inside. Okay, it doesn't matter. So I have negative 2. Now if you look, we have x, and of course we have x here. So using the laws of indices, which states that when you have the same power, the same base, you add their powers. Okay, when you have the same base, you add their powers. So the power of x here is 1. The power of x here is n minus 1. So of course, using the law of indices that states that when the bases are the same, the multiplication law of indices that when the bases are the same, you add their powers. So x being multiplied by x to the power n minus 1 gives you x to the power of n minus 1 plus 1, which gives us x to the power of n. So this is what you're going to have afterwards. So using this, I'm going to have summation of from n equals 0, n equals 1 to infinity n a subscript n x to the power of n. plus alpha bracket alpha plus 1 summation of n equals 0 to infinity a subscript n x raised to the power n all equals to 0. So using that same procedure, I want to apply it in this term using that same procedure that we used in this place. So I can confidently say that this whole term is something as saying, since we have x squared, we multiplying this whole stuff means x squared times, using our law of indices as well, x raised to the power n minus 2. So it's something as saying x raised to the power n minus 2 plus 2, which gives us x raised to the power of n. So this whole summation can be rewritten as the summation of everything here. So from here, we have arrived to something better. So our aim is to make all the powers to be the same. As you can see, the power of x here is to the n. Of course, this one is to the n, and of course, this one is to the n. But the power of this other x is to the n minus 2. So our aim is to make all the powers to be the same. So making the how are we going to make that possible? So we are going to make that possible by, let's say, let n only for this summation, only for this sum, let n equals n plus 2. So if you should let n equals n plus 2 to this, only to this sum, we can as well help make x to the power of n. So, but when we let n equals n plus 2, it's going to affect every other n that we have in this summation. So, let's go ahead and do it. So, from there, we have that the summation of, now this, since n is equals to n plus 2, this n is solved as n plus 2 is equals to 2, which means that n is equals to 0. So, the limit changes from n equals 0 to infinity. So whenever we see n, we impute n plus 2. So we have n plus 2. Of course, if I put n as equals n plus 2 here, what I'm left with is n plus 1. A subscript. Of course, this n is also going to be affected. So we have a subscript n plus 2. X raised to the power of, we have, I said when let n to the n plus 2. So we have to this power, since this n is something as n plus 2. So we have n plus 2 minus 2, which we are left with only n. So here is n. So we have been able to achieve our aim. And of course, I'll write down everything. I'll bring down to that one. So n equals to infinity, n bracket n minus 1, a subscript n, x raised to the power of n, minus 2, summation of from n equals 1 to infinity, n, a subscript n, x raised to the power of n, plus alpha bracket alpha plus 1, summation of from n equals 0 to infinity, a subscript n, x subscript n, x raised to the power of n, all equal to 0. So, but how can we create our recurrence equation? So our recurrence equation can only be created if all the limits of the summation are the same. So if you check, the limit of this first summation is to the 0, this one to the 2, to the 1, and of course to the 0. So our aim here is to make all the limits, the lower limits, to be the same. Since we have been able to make our x to the n to be the same. So let's make our limits to be the same. So how can we make our limits to be the same? We can only make that by, let's expand this series. We can only be made possible by expansion of each of these series. So since my maximum limit is 2, so my aim is to increase these other lower limits to 2. Okay? So how can I achieve that? I can only achieve that by expansion. So when n is equal to 0, so whenever you see n, you impute 0. So when n is equal to 0, so we have 2, because 2 plus 0 will give me 2. This one we have 1, because 1 plus 0 will give me 1. So we have 2 multiplying 1. And then in this side, we have a subscript when n is equal to 0. So when n is 0, that means a is only remaining 2, x raised to the power of 0. So the first term we have here is 2 times 1, we have 2. A2, of course, x is equal to 0 is going to give us 1. So that's the limit we have here. Now, the next one is when n is equals to 1. So when n is equals to 1, we have that what we have here is 1 plus 2, which is 3. 1 plus 1, which is 2. 1 plus 2, which is a subscript 3. And of course, x is to the power of 1. So by multiplication, 3 times 2 gives us 6. A3, of course, x is to the power of 1 is something as x. So, since we have achieved our first term, this is when n is equal to 0, and when n is equal to 1, we can comfortably say, instead of me to write the next term, which is n equals to 2, I can start the series from n equals to infinity, n plus 2, n plus 1, a subscript n plus 2, x raised to the power of n. So I wouldn't have to touch this other one because that is the maximum limit. So I can bring it down by saying summation of n equals 2 to infinity, n bracket n minus 1, a subscript n, x to the power of n. Now, looking at this other series, you can see that it starts from 1. So let's increase it. So when n is equals to 1, of course, remember 2 is multiplying this whole summation. So we have -2, of course, use -2. Now when n is equals to 1, so -2 times 1 times a subscript 1, of course, x raised to the power of 1. So what we have here is -2 a1x, okay? So we have -2 a1x from here. Then instead of me to write when n is equals to, I will just bring it down by saying minus 2 summation of from n equals 2 to infinity n a subscript n x raised to the power of n. So the next one we are going to touch, is the last one. So it starts from 0. So our aim is going to be how to increase it from 0 to, of course, 2. So as we did from the previous ones, we are going to apply when n is equals to 0 and of course when n is equals to 1. So when n is equals to 0 in this term, we have that, of course, we have alpha bracket alpha plus 1. So when n is equals to 0, we have a naught and x raised to the power of 0. So the next thing we have here is plus alpha bracket alpha plus 1 a naught, because x raised to the power of 0 will give me 1. Now when n is equals to 1, so if n is equals to 1, we have that alpha bracket alpha plus 1. When n is equals to 1, we have a1x raised to the power of 1. So from here, we have that this becomes alpha bracket alpha plus 1 a1x. Okay, so this is the when n is equals to 0, when n is equals to 1. So instead of me to write for the series of when n is equals to 2, I'm just going to bring down this equation by saying plus alpha bracket alpha plus 1 summation of n equals not 0 this time but 2, because I've done for 0, 1. So this is 2 to infinity a subscript n x raised to the power of n all equal to 0. So with this equation, I can form my recurrence equation. Okay, I'm going to use that to form my recurrence equation. So how am I going to form my recurrence equation? I'm going to do that by comparing the coefficients of the powers of x. So I'm going to compare the coefficients of the powers of each of the x, and I will bring everything out. So by comparing the coefficient of the powers of x, I can see, let's start with the one that have x raised to the power of 0. So in this case, this has x raised to the power of 0, and of course this one also have x raised to the power of 0. So by comparison, we can comfortably say that 2a2 plus the next one, alpha bracket alpha plus 1 a naught is equals to 0. Okay, so this happens when x is raised to the power of 0. So this is when x is raised to the power of 0. So let's check when x is to the power of 1. Okay, like in this case now, x has the power of 1, x has the power of 1, and x also have a power of 1. So bringing everything out, I have 6a3 minus 2a1 plus alpha bracket alpha plus 1 a1, okay, all equals to 0. So this is when this happens when x is raised to the power of 1. So the next one is when x is raised to the power of n. So when x is to the power of n, the only thing I'm going to take from there is the implications of all the terms. Just take all the implications, all of them, all the implications, okay? So taking all my implications, we have my inputs, we have that n plus 2, n plus 1, a to the n plus 2, minus n bracket n minus 1, a subscript n, minus, so of course 2 n a subscript n, 2n a subscript n, then with the last one plus alpha bracket alpha plus 1 a subscript n, all is equal to 0. So this happens when x is raised to the power of n. So that happens when x is to the power of n. Okay, so from here, so the next thing I'm going to do is make the maximum subscript the subject of the formula. So let me call this equation 1, let me call this equation 2, and of course let me call this equation 3. So let's make the maximum subscript the subject of the formula. So from equation 1, the maximum subscript is, of course, is a2. a2 is greater than a0. So we have that 2a2 is equals to negative alpha bracket alpha plus 1 a1. So to get our a2 of course is equals to minus alpha bracket alpha plus 1 a0 divided by 2. So this is the value of a2. So let's from equation 2, from equation 1. So from equation 2, we are going to make the maximum subscript, the highest subscript, the subject of the formula. So from here, we can see that our highest subscript is, of course, a subscript 3. So by making this subject of the formula, we have that 6a3 is equals to 2a1. Okay, so from equation 2, we are going to make the maximum subscript the subject of the formula. So from this equation 2, we know that the highest subscript is 3. So we are going to have 6a3 is equals to 2a1 minus alpha bracket alpha plus 1 a1. Okay, so that's what we have here. So Okay, so the next one is to make the A3 the subject of the formula. So A3 is equals to 2A1 minus alpha bracket alpha plus 1 A1 divided by 6. So since A1 and A1 are the same, let's factor out the A1. So if you factor out the A1, we have that A3 is equals to 2 minus alpha bracket alpha plus 1 all being multiplied by A1 divided by 6. So this is for A2, this is for A3. So this now from equation 3, from equation 3, we have that from equation 3 we have that, okay, which one are we going to make the subject of the formula? So as you can see, n plus 2 is greater than n. Sorry, it's greater than, of course, yes, n plus is greater than n. So we are going to make a subscript n plus 2 the subject of the formula. So by making that the subject of the formula, we say n plus 2 brackets n plus 1 a subscript n plus 2 is equal to, taking this over, we have n brackets n minus 1 a subscript n plus 2n a subscript n negative alpha bracket alpha plus 1 a subscript n. Okay, so and if you look at this one, you see that it has a like term, which is a subscript n. So let's factor out a subscript n. So we have that n plus 2, n plus 1, a subscript n plus 2 is equals to, we have n bracket n minus 1 plus 2n minus alpha bracket alpha plus 1 all being multiplied by a subscript n. Okay, so we have to make our a subscript n plus 2 the subject of the formula. So making a subscript n plus 2 the subject of the formula, you have to divide by the coefficients, which is n plus 2 and n plus 1. So a subscript n plus 2 is equals to n bracket n minus 1 plus 2n minus alpha bracket alpha plus 1 all being multiplied by a subscript n divided by n plus 2 n plus 1. So I am safe to say that this is what we call, this equation is what we call the recurrence. We call this the recurrence equation. Okay, so we call this the recurrence equation, and this equation is applied from when n is greater than or equal to 2. Why do I use when n is greater than or equal to 2 is from the previous ones that we got, we see that the maximum subscript that we have is 2. So that's why it's going to be greater than or equal to 2. So from here, you can form as many recurrence equations as you can, and of course, get the final answer. So this is the conclusion of this. So we are going to solve an example and then we'll see how this works.